Hello, my name is Lee Spector, and this is the tutorial on push at the 2021 GECCO conference. This video is a backup video or alternative video. The tutorial is intended to be presented live online, and the backup video is in case something goes wrong during the conference with the online presentation system, or in case somebody wants to watch it asynchronously. In this backup video, I will be presenting the same material as in the live tutorial, except there's a section in the middle of the tutorial when I will be giving a bit of an interactive demo and taking questions about the demo and suggestions and so forth, and that I'm going to skip in this video. So there's a little bit of information about me on this slide. You can pause and read if you like. And here's the outline of what we're going to discuss today. I'm going to present the push programming language and the reasons that you might care about it, which all involve using this programming language as the language within which evolving programs are expressed. So the push programming language is not a programming language for humans to write programs in. It is a programming language for programs to evolve in. So it is designed as a substrate for evolution of programs. The specific features that make push a suitable language for program evolution are the ways that it handles types and the ways that it handles control structures, and that it does so without syntax. The mechanics of these mechanisms of programming languages are usually handled through syntactic differences in different kinds of structures in the code that you write. But by doing this without syntax, we provide a substrate that is more suitable towards random variation and selection. After going over the basics and walking through how the language works and looking at different kinds of programs and how they're expressed in the language, we will look at the process of evolving push programs. I will conclude with some discussion of some kind of novel things that you can do with push that it's very hard to do with other program evolution mechanisms, including ways in which the evolution of programs, the mechanisms by which programs evolve, can themselves evolve during an evolutionary computation run. So there's a kind of metagenetic programming that is relatively easy to do in push and harder to do in other frameworks for program evolution. And in fact, that work on evolving the evolution of programs was one of the motivations for developing push in the first place. And so even though most people most of the time don't want to do something like that, I do want to show you what that's all about. Okay, so let's talk about the push programming language. It is, as I said, a programming language for programs that evolve, not for programs that human beings write. And the key idea of the push programming language, as you might have guessed from the name of the language being push, it involves stacks. And on a data stack, the standard operations are pushing things onto the stack and popping things off a stack. In the push programming language, all data flows between instructions via per type stacks, not via syntax. Now, some of you may be familiar with other stack-based programming languages, like the Forth programming language. That's an old and important programming language in which there is a data stack that is used for communicating between instructions. The primary difference, maybe there are more than one, but the biggest difference between push and Forth and other stack-based languages is that in push, there is a separate data stack for each data type. And this is one of the things that's going to make push programs safe for random variation. The idea is that each instruction takes whatever arguments it needs from the appropriate data stacks, the stacks of the appropriate types, And because that's built into how every instruction works, they can never get arguments of the incorrect type. So every instruction gets its arguments from stacks of the appropriate types, and whatever results it produces will be pushed onto stacks of the appropriate types. And this data flowing via stacks is really what replaces syntax in the push language. Normally, in a kind of programming language as most of us humans write programs in, the way that we specify what arguments go to what instructions is their adjacency in the text of the code, right? Depending on the language you're using, you might have the name of a function and then within parentheses, the literal or variable that provides the data that is provided as input is an argument to that instruction or function. And then perhaps that function call returns a value, and it returns it to what is syntactically maybe to its left on the other side of an equal sign, depending on the language. It is the syntax in a normal programming language that's designed for humans that determines how the data flows. But in push, it is the stacks. So an instruction always gets its inputs from stacks and always provides its outputs to stacks. And those are per type stack. There's a separate stack for each data type. And that is how data flows. This arrangement allows us to have a language which has a truly trivial syntax. Pretty much any arrangement of instructions and literals and balanced parentheses is a syntactically valid push program. And yet, because of some of the specific ways that push handles code itself as a data type, the push language provides for rich data and control structures. Normally, those two things are linked in human programming languages. Rich control structures usually come with some new syntax, not in every programming language, but in many of them. And so you usually get complex syntax along with your complex semantics. But in push, these things are divorced so that you have, no matter what, you have a completely trivial syntax, almost no syntax really. And yet, because of the way that code manipulation instructions work, which we'll cover shortly, you can have rich data and control structures. All right, those 3 bullet points are really the key ideas of push. And if you followed me so far, I think that you have an idea what this push language is like, and maybe some inkling of why it's a nice substrate for program evolution. PushGP is what we call any genetic programming system that evolves push programs. And over the years of the development and refinement of push, there have been many different PushGP systems. So it's not really just one specific system. It's any push evolving genetic programming system we call PushGP. There have, in fact, been implementations of push and PushGP in many host languages. Some of the initial work was done in Common Lisp, but people have developed push interpreters and PushGP systems in at least the languages I've listed here. Notably, Python and Clojure, those are 2 languages in which there is a fair bit of active development of push and PushGP work. My research group does most of our research in Clojure, which is a Lisp for the Java virtual machine. But we also have a system, actually several systems in Python. And people have developed push and PushGP systems in all of these other languages listed here, and maybe more. The key ideas of the push language, though, are actually pretty simple. And I'm not going to advocate here that you necessarily use any of the systems that my group or any other group has developed, although if you want to, there are many that are available, and there's some pointers at the URL I posted here, and at the end of this talk there are some other pointers, and you're certainly welcome to grab one of those implementations and incorporate it into your work. However, what I hope to do over the remainder of this tutorial is to show you the core ideas with enough clarity that you, if you're a reasonably seasoned programmer, could sit down in an afternoon and write a bit of a push interpreter in whatever language, whatever framework you work in, and use that for program evolution. The ideas are really quite simple. Once you can implement stacks and a few other basic things, it's pretty easy to put together a simple push interpreter. And on top of that, you can then build whatever program evolution system you prefer. So if you don't, if you don't like a generational GP system and you'd rather have a steady state system, or you want to evolve programs within a Unity framework for your game, or you have a C++ framework, well, there is some C++ push thing that's already been written, but you might find it even better to write your own. And my primary goal in this tutorial is to show you the core concepts clearly enough that you would see what it would take to do that, and in fact that it would not take a great deal. Okay, so before we dig into examples of the language and showing how it works, let's talk about a little bit more about why you might want to evolve programs in push as opposed to symbolic expressions of the Lisp variety, or program trees that are often used in tree-based genetic programming. There are a lot of languages that are used for genetic programming. Historically, much of the early work was done in Lisp-style symbolic expressions with prefix notation and producing what we think of as program trees. And that's a powerful, wonderful representation. However, it has some limits, or some rough edges. One rough edge in the traditional tree-based representation is that if you're going to do random variation, moving values around and moving subtrees around, and if you have multiple data types, you have to think a lot about how to avoid type errors. You have to make sure that every function gets the right number of arguments of the right types. Now, there are, of course, ways to do that. Strongly typed genetic programming, as it is sometimes called, is one way of doing that, where you specify the type requirements and return value types of every function, and you specialize your genetic operators to attend to those types. That can add complexity to the implementation, and it can also limit the search space in some non-trivial ways. However, with push, adding additional data types is much more straightforward and has no such impact on genetics. Arbitrary control is also something that push provides that is somewhat difficult to attain with tree-based or many other representations. So while people have developed looping and conditional structures in tree-based program representations used for genetic programming, it's quite a bit trickier to say evolve something that uses some notion of coroutines or different numbers of automatically defined functions that take different numbers of arguments or different types of arguments and so forth. And again, people have developed ways to do this in tree-based systems and in other program representations. But push also gives you that without doing anything extra. The mediation of all control via stacks makes it so that you can get arbitrary control structures in a quite straightforward way without adding anything except an instruction that manipulates something called the execution stack, which we'll get to shortly. Another issue with traditional program representations for genetic programming is when you want to evolve programs that complete multiple tasks. Okay, so if you want a program that does not just return a number, but maybe returns a list of strings and a number, and performs another task that involves different data types. And the same program is supposed to do multiple things with multiple modes of input and output. Again, in push, this is going to be completely straightforward, whereas in many program representations used for genetic programming, it's quite tricky, and you have to extend the system in some ways. In a program tree, typically each node returns a single value to its parent node in the tree, right? And so if you're doing multiple tasks and returning multiple values, you have to think about, are you returning some kind of collections of values, or are you producing some of those effects via side effects rather than the return values of the nodes in the tree, and so forth. Again, that can be tricky in many representations. For evolving programs that perform multiple tasks, I also note here that lexicase selection, a particular parent selection mechanism in genetic programming, also developed within the framework of push, seems to be quite useful. It's independently useful, actually, of push. There is another tutorial at this conference at GECCO2021 on lexicase selection being presented by Tom Helmuth and Bill LaCava. I strongly recommend that you check that out as well. But that can be useful in conjunction with the ability of a system to perform, to evolve programs that perform multiple tasks. And then finally, again, and I list it as optional here, is that the expressiveness of the push language makes it possible, among other things, along with evolving programs that use multiple types and arbitrary control structures and that complete multiple tasks. It also allows you to evolve programs that express their own methods of reproduction and variation. Okay. So normally in genetic programming, the methods of reproduction and variation are provided by the system or by the programmer. That means, how do you do mutation? How do you do crossover? How do you do mate selection, and so forth? The fact that a push program can, among other things, produce and manipulate code allows you to do some fairly exotic things with evolving self-reproduction and variation methods. Again, this is kind of metagenetic programming. And I'll talk a little bit about a particular kind of that called autoconstruction later in the talk. Again, though, you may want to use push for reasons that have nothing to do with that. Just if you want to evolve programs that might make use of multiple types and arbitrary control and perform multiple tasks, then I think you want to check out push, even if you have no interest in evolving the reproduction and variation methods. All right, so at this point, we're going to actually dive in and look at a push program interpretation. Okay? And first, we're just going to take a look at what the push virtual machine looks like. So a push program gets executed on a virtual machine that consists of a set of stacks, of data stacks, one for each data type, as I mentioned earlier. However, there is one additional stack that is always there, called the Exec Stack. And the Exec Stack contains code, and it is the mechanism by which the push program is executed. So it acts in many respects just like the other stacks, except the program interpreter treats it specially in executing the program. Now, I should note also, if you look at old push papers, the original push ideas from the very beginning of the 21st century, the first few years of push, there was no exec stack, and the way programs were interpreted was a little bit different. Some of the ideas still hold, but the language has developed quite a bit over the years, and in particular, the exec stack was added, first appeared in print, I believe, in 2005 in a GECCO paper. And that was then called Push 3 is what we called that version of push. And the exec stack was invented by Martin Kaiser And he came up with this idea, which was such a great idea and really helped to make push much more flexible and powerful. All right, so what we see here is a sort of snapshot of a push virtual machine during the execution of a program. And what you see on the exec stack is a bunch of code. We'll talk about how it got there and how it executes in a minute. But we see on the integer stack a bunch of integers. So 7 is on top of the stack, and -20 is below that, and 100 is below that. And on the Boolean stack, we see a stack of Boolean values. And on the string stack, we see some strings. And you can have as many more stacks as you want. Okay. And the whole point here is that whatever stacks, whatever types you want your program to be able to manipulate, you create a data stack for it. And there will be instructions for the data of that type and perhaps on combinations of data types. Okay. Now, how does a push program execute? This slide is the entire interpreter. So when I say that you can implement a push interpreter in an afternoon, probably in any programming language that you're fluent in, this is the key thing you have to implement, is just this one slide. And this is how you interpret a push program. And here's, oh, I guess actually, let me mention for a moment, go back to this slide and tell you that all push programs are just sequences of instructions. So we have here integer mult and Boolean and, those are instructions. And you can also have balanced pairs of parentheses that can have instructions, oh, and literals also. So 3 is a literal, string dupe is an instruction, and parentheses around those, that is a push program. So a push program is any instruction or any literal or any parenthesized expression containing other push programs, which can be literals and instructions and parentheses and so forth. And of course, they can be nested. Okay, so here's how you execute a push program. First, you push it onto the exec stack. So you can typically, you could start with a preloaded virtual machine that has stuff on the stacks, but for now, we'll assume you start with empty stacks. So you would start with something like this, but with nothing on any of the stacks. Then to execute a push program, you push it onto the exec stack, and then you go into a loop. And in this loop, while the exec stack isn't empty, and we haven't hit the step limit, about which I'll say more in a moment, we pop the exec stack and we do the top, the thing that we popped. If it is an instruction, we execute that instruction. And if there are insufficient arguments for that instruction on the stacks from which it should take its data, we do nothing. So for example, there's an integer add instruction that pops 2 integers, adds them together, and pushes their result back on the integer stack. If you try to execute an integer add instruction and there are not 2 integers on the top of the integer stack, it just does nothing. Okay? And that's an important piece of the no syntax aspect of push. The reason that any scrambled bunch of literals and instructions and balanced parentheses is always syntactically valid and can always be executed is, first part is that everything always gets its arguments from the stacks of the appropriate types and pushes the results onto the stacks of the appropriate types. And the other part is, if there aren't arguments of the appropriate types on those stacks, it just does nothing. It no ops, okay? So if it's an instruction, you execute it. If it's a literal, you push it onto the appropriate stack. So if -7 is on top of the exec stack, when you're coming through this loop, you push it onto the integer stack, okay? If it is a list, so if it is surrounded by parentheses, then you push its elements back onto the exec stack one at a time, okay? So to execute a parenthesized expression, you basically remove the parentheses and push all the items back onto the stack. This will be more clear as we walk through an example. So let's look at this state that we just saw before, which I said was a snapshot in the middle of a push program evolution. And let's see what happens if we continue execution from this point forward. So at this point, if we're going to go into this while loop, so the exec stack isn't empty, and we haven't yet hit the step limit. What do? Well, we're going to pop and execute integer molt. So we pop integer molt, and then we do it. And since it's an instruction, we execute it. And what integer molt does is it takes two integers from the integer stack, multiplies them, and pushes their product back onto the integer stack. Okay, so we get 140. Okay, so we went from there with integer molt on top and 7 and minus 20 there to this state where we have minus 140 on top of the integer stack. Now Boolean and gets executed, and that takes two Boolean values and pushes their and, which will be false here because we have true and false arguments, which true and false is false, right? So we end up with false there. This next element on top of the exec stack is the list with 3 and string dupe. And because that is a list, it's just going to get unwrapped and the items are going to get pushed back onto the exec stack. Okay, so it went from there to there. Now we execute the 3. Since it's a literal, it just goes onto the appropriate stack. Now we're going to execute string dupe, which takes one thing off the string stack and pushes 2 copies of it, okay, duplicates it. So we end up with that. And then integer add is going to add 3 and minus 140 to get 137, minus 137. Now the exec stack is empty and we are done executing this program, okay? So that's a basic push program. It's not an interesting one. I want to say a few more things about this particular final state. One is the exec stack is empty, but there's a bunch of stuff on other stacks. What is the answer? What is the result? That is up to you. The push language specifies what happens when you execute it. What ends up on the stacks, you can decide what you care about there. So very frequently, suppose you're doing a genetic programming for symbolic regression. Since I have integers here, but I don't have floating point numbers here. Let's say it's integer symbolic regression. And suppose you are trying to evolve a program that produces for some inputs a particular integer value, then you can just say whatever is on top of the integer stack at the end, that is what I will call the result. And you will evolve programs that leave the correct value on the top of the integer stack, okay? And you might ignore everything else. But it depends on what kind of problem you're trying to solve. But you end up with this complete state of whatever is on whatever stacks. And depending on the application that you're working with, you may say that the result is, typically we say the result is what is on top of some output stacks that are the values we care about, but it might be multiple stacks. It might be multiple values on a stack and so forth, okay? One other thing I wanted to say is we did empty the exec stack here. And as I mentioned, you might want to, well, you will end your execution earlier if you hit this thing I call the step limit. As you're going to see shortly, it's very easy to make arbitrary control structures in push. And the downside of that, of course, is that it's also very easy to make infinite loops. I mean, it depends what instructions you provide, how easy that is, and what you want to do about it is up to you. But it is possible to make programs that loop infinitely. So we need a way to stop their infinite running when we're trying to evolve programs that terminate. With push, you always provide some limit on the number of execution steps, the number of times through that while loop. And you might provide some very high value. And if you hit that limit, you could do a variety of things. You could impose a penalty or not. Again, that's up to the rest of your genetic programming system, what you want to do about that. But you provide, let's say, I'm going to go for 1,000 steps. And if I do 1,000 steps and I still have stuff on the exec stack, I just stop anyway. Okay, so that's what it means here on these top of this while loop. Says while exec isn't empty and we haven't hit the step limit, we do this stuff. Okay, so if it is empty, if you do hit the limit, then you stop. Excuse me. Then you stop. Notice though that a nice thing about hitting the execution limit with push is even though you stop, you still may have values that you can use on the rest of your stacks. Okay, so in many other evolution programming languages, if you terminate, say you're evolving tree-based programs, and suppose they do have looping structures in them, and maybe you've set it up such that it is possible to have, say, infinite recursion or an infinite loop, and you impose some execution limit, it may not be very clear if you hit that limit what the result of the program execution would be. But here in push, no matter why you stopped execution, you have your data stacks, and perhaps you can say, well, I hit the limit, but still I'm going to say the answer is -137. That's up to you. Okay, let's look at executing a full program. I showed you just a moment ago, starting in the middle of an execution. Well, here's a very simple program for adding 1 and 2, and we're going to execute it from scratch. So we do that by first starting with empty stacks, loading it onto the exec stack, and then we enter that loop and do the standard thing, which is, well, we pop the top thing. In this case, it's a list, so it gets unwrapped. Okay, then we execute the 1, then we execute the 2, then we execute the integer add. We've got a 3 on top of the integer stack. The exec stack is empty, so we are done with execution. Okay. Now, here are a bunch of other relatively simple examples, just to give you a feel for how the language works. 1 to integer add, we just saw, leaves 3 on the integer stack. True, false, Boolean, or Boolean not leaves false on the Boolean stack. So the or of true and false is going to be true. And then the Boolean not takes 1 argument off the Boolean stack and pushes its not. So that will become false from being true. 3, 5, integer LTE. So LTE, this is some terminology from John Koza's early work, standing for less than or equal, leaves true on the Boolean stack. So integer LTE takes 2 integers, compares them, and pushes true if the first is less than or equal to the second, and pushes false otherwise onto the Boolean stack. Okay, so this takes integer inputs and Boolean output. I'm going to take 2 things from the integer stack and push 1 thing to the Boolean stack. Again, if there weren't 2 integers on the integer stack, this would just be a no-op. Okay. Now, this one's a pretty fancy one because we do what we did before, 3, 5, integer LTE, and then we have an exec instruction. Now, exec instructions provide a lot of power. They manipulate things on the exec stack, which is going to change what gets executed next, because the basic mechanics of the push interpreter are that you take the top thing from the exec stack and you do it, right? Well, if doing it changes what's on the rest of the exec stack, then you're changing the future of the computation. And that is the germ of the power of push, of the power to implement arbitrary control structures and so forth. Okay, so execif is one of the simpler things. It requires 1 thing on the Boolean stack and 2 things on the exec stack. So there are going to be 2 things below it on the exec stack. If it's not going to no-op, there have to be 2 things below it on the exec stack. And depending on the value on top of the Boolean stack, we're either going to remove from the exec stack the top item or the second item. Okay, so if there's a true on the Boolean stack, then we're going to remove the second item from the exec stack. And if there is a false, we're going to remove the top item. Okay? What that means is, depending on what's on top of the Boolean stack, the way the exec stack looks at the next step of execution is just going to have one or the other of those things that were on top of the exec stack when exec if was being executed. Now, what is going to be under exec if when it executes? Well, it's going to be those next 2 parenthesized expressions. That's what's going to be under it. And why are those things going to be under it? Normally with the stack-based language, you think of the arguments coming first, like 3 or a 1, 2 integer add. You think the arguments, get pushed first, and then the instruction pops them and does them. Well, that's true of all the stacks except the exec stack, because of the way lists on the exec stack are unwrapped, which we've seen a couple times already. So when you think of how this whole program is going to be executed on the exec stack, when it gets unwrapped, the 3 is going to be on top, 5 is going to be under it, the integer LTE is going to be under that, the exec if is going to be under that, then the 1 yes expression is going to be under that, and then the 2 no is going to be under that. The 3 gets executed, the 5 gets executed, integer less than or equal to pops the 3 and the 5 and pushes a true. Then we've got the exec if on top of the exec stack, and below it is the 1 yes, and below that is the 2 no, right? And since there will be a true on top of the Boolean stack when that exec if executes, it is the 2 no, the second thing on the exec stack that's going to be deleted. All that will be left on top of the exec stack at that point is the expression 1 yes. When that gets unwrapped, then the 1 will be executed and end up on the integer stack, and then the yes will get executed and end up on the string stack, and you're going to end up with yes on the string stack and 1 on the integer stack. Okay. So this one, a little more complicated, but I hope that you can see the power of this exec if, but also its simplicity. It's not a complicated thing to implement. It just, like any other push instruction, takes some arguments from stacks. It just happens that one of those stacks it's taking things from is going to be the exec stack, and it does some things to the stacks. In this case, it is going to delete something from the exec stack based on the Boolean that it reads. Okay. All right, so that should give you a feel for the basics of push program execution. Now, what instructions do you want to have in your push interpreter? Well, you may want special purpose instructions related to your problem domain. You may want math for your integer and your floating point numbers. You may want the equivalent of a standard string library to operate on your string data type, maybe combinations of strings and integers and so forth. But in addition, you probably want to have for every data type, or most data types anyway, some standard stack manipulation instructions. And these are quite similar to basic instructions in languages like Forth, okay? So it's just generally handy in a stack-based language to have a dupe instruction that duplicates the top item of the stack. And in push, because we have a separate stack for each data type, you probably want one for each data type. So you'll have an integer dupe and a float dupe and a string dupe and so forth. Also an exec dupe, by the way. And an exec dupe is going to whatever code follows it in the program is going to get duplicated when it's executing. So an exec dupe is a simple do twice kind of loop. You want an instruction that tells you whether or not a stack is empty, whether or not the top 2 items on a stack are equivalent. You'll want to have a way to flush the stack to empty it, and so forth. Okay. Swap the top 2 items. And yank and yank dupe are things for deep stack access. And stack purists might say, oh, a stack you can only access the top of. And if you don't want to be able to access deeper, then don't use yank or yank dupe instructions. But yank and yank dupe are ways of reaching deeper into the stack with an integer index and yanking something from deep into this in the stack from an integer index to the top of that stack. And yank actually pulls it out of where it is, and yank dupe pushes a duplicate on top of the stack. All right, here are just some selected instructions to give you the feel for the kinds of things that most push interpreters include. So some integer instructions for adding and decrementing and dividing and comparing, so greater than. Conversions, integer from string. We'll read a string from the string stack and push an integer. It is up to you how you want to make that work. If you implement something like that, for example, does it, if the string doesn't have number of characters in it. What are you going to push? Maybe you'll just no-op. You have options there, okay, and so forth. Boolean instructions, string instructions. Again, the push language concept doesn't dictate any particular instruction set, but you can provide sort of the standard toolkit that any programming language provides for standard data types as instructions that you can make available for program evolution. Exec instructions are a little different. Those instructions for the other types are more or less exactly what you would have in any programming language. Well, here we can write things that manipulate the exec stack that are quite similar to what you have in terms of control structures in traditional programming languages, but it's easy to do other things as well. So we looked at exec if, exec when is usually the same thing, except only one, only if it's true you do it. You don't have a false clause. You can have general loops, and we have something called exec do star while that will provide something like a regular while loop that will keep evaluating an expression until it becomes false, and then it will leave the loop. The way that is usually implemented, by the way, is that it will take the next thing on the exec stack, push it back onto the exec stack with an exec if under it, so that it will end up when this thing goes into the next cycle of the execution loop, it will end up evaluating that expression, and then depending on whether or not a true or a false, whether or not a true was left on top of the Boolean stack, it will or won't do the body of the loop, which this instruction will have put below that exec if, with added to it another call to the while loop, so that you get this kind of recursive execution on the exec stack without changing anything about the standard execution cycle. So looking at how to implement that, I think it would be quite instructive. I'm not going to go into the details of that, but you can look in any of the implementations or any of the papers we've written about that to look at how you do that. You can also get things that are like for loops, things that loop over structures. These are all examples of instructions that we do have in our implementations, and you can also have combinators out of which arbitrary control structures can be built. All right, I don't expect you to be able to read this, but this is a bunch of the instructions from one of our systems, just to show you that in this framework, often in genetic programming, people will develop systems and apply them to a problem in which they only provide a small number of instructions, which are the ones they think are going to be most useful. In push systems, it's quite typical to provide a very large instruction set and let evolution sort that out. There's research on helping it to sort it out, what we call different genetic sources. But typically our systems have very large numbers of instructions, and they work quite well despite that. And so you can provide things for all the data types and stack manipulation and domain-specific functions and so forth. Okay, some of the kinds of instructions that we have developed and are in many of our implementations that I haven't gone into in detail here, but I want to mention are listed here. One is input instructions. So, if you're doing symbolic regression and you're evolving a function of 3 inputs that produces 1 floating point output, how do you specify the inputs before you run the program, right? So for these 3 input values, what does the program produce? You could do that in a variety of ways. One idea is to preload the 3 inputs onto the stacks. What we usually do is instead provide special instructions that push input values, okay? So we would typically have an instruction called in1 and in2 and in3, and wherever they appear in the program, they would push the current value for that input instruction. And typically we actually implement that by making another stack called input that just has the items that will be used for the input instructions. And we don't provide any of the standard stack manipulation stuff for the input stack. So that's just a bunch of constants sitting there, and these instructions just push those constants onto the exec stack from where they get pushed onto the stack of the appropriate type. Print instructions, so instead of returning values, sometimes you want to have outputs that are produced as in the style in which you produce output with print statements in traditional programming languages. And we typically implement that as a write-only stack that you can send stuff to. That again, for that one, we don't have any instructions that take anything off of it. So it's sort of a one-way stack. Things get pushed onto it, and then at the end of program execution, whatever is on there is what has been printed. Okay. We've provided methods for associative storage via tags. So this is sort of local variables. There are mechanisms that have been developed for having modules that in push that execute in local environments and from which they can return values. And that involves stacks for environments and for return values. And as I mentioned, there are execution limits, and that can lead to programs terminating either normally or because the step limit was hit. But there are other limits that you may want to have as well. This holds true of every genetic programming system. Evolution can produce programs that produce enormous values, or giving you integer overflows or float underflows, or lists that grow exponentially and so forth. And so in any genetic programming system that is sufficiently expressive, if it's going to be possible for programs to misbehave in those ways, then you're going to want to impose some restrictions to deal with those situations one way or another. Okay, so much of the recent work on push has been done with this system called CLOJUSH, which is a clojure-based push and PushGP system. And I'm not necessarily recommending that anybody watching this tutorial use CLOJUSH. It has been the environment in which a lot of ideas have been developed and a lot of experimentation has been done. But in part because of that, it's accumulated all sorts of bizarre stuff, some of which is useful and some of which isn't. The stuff that I'm presenting in this tutorial are really the core ideas. We have several other systems I'll mention at the end of the tutorial that are much simpler and stripped down, that just do the stuff that we know is useful. And again, my recommendation is actually that you try to understand the core ideas and roll your own and ask for help from somebody who's done some push if you need it, or use probably one of the other libraries. But I'm showing you this CLOJUSH GitHub page because the examples I'm about to show you are done in CLOJUSH. The different push dialects also sometimes have different conventions for naming instructions, because the host languages maybe make it, more convenient. Some you can name symbols that have dots in them and some you can't. And so you have to use underscores and so forth. So there's some variation in the ways things are named and so forth. And the examples I'm about to show you are CLOJUSH examples. Okay, so here within CLOJUSH, you can issue a call, and these are going to look like Lisp calls because Clojure is a Lisp. You can call the run push function on a push program in a particular starting state, and this make push state gives you an empty one. So it gives you an empty push state with nothing on any of the stacks. And if you call this, then the sequence of things that's going to happen on the stacks is as follows. Well, there are other stacks as well, but I'm not showing them because nothing exciting is happening on them. But the exec stack starts with, so these outer parentheses are the stack itself, and it has one thing on it, which is the entire push program, which is open parenthesis 1, 2, integer add, close parenthesis. So the whole thing was pushed onto the exec stack. Then after one step of execution, that stack is unwrapped. And what that looks like here is now the stack itself, the top element, the first element in this list is 1, the second element is 2, the third element is integer add. We then execute the 1, which causes it to be pushed on top of the integer stack. So the stacks here are being represented as lists with the top of the stack being first, right? So now we have a 1 on top of the integer stack. We execute the 2, we push the 2 on top of the integer stack. We execute the integer add, that's gonna pop the 2 and the 1 and push the sum, which is 3, and the exec stack ends up empty, and this is done, okay? Here is a more complicated program. 2, 3, integer mult, 4.1, 5.2, float add, true, false, Boolean, or. Run that on an initially empty push state, and we're going to end up with an empty exec stack after that is all done, and 6 on the integer stack, 9.3 on the float stack, and true on the Boolean stack. Okay. This is in words. This is the same as the previous one, except I scrambled things a bunch and added a bunch of garbage. And the point of this is we end up with the same state. So you see between these two slides, the same final state. But several of the operations, when they first get executed here, when they get executed, become no ops, because this Boolean and is now going to be executed when all that is on any stack other than the exec stack is the 2 on the integer stack. There's not going to be any Booleans in the Boolean stack, so that's just no ops. Okay. Also, a difference here is that some of the operations here on the integers happen first, and then the floats, and then the Booleans, and here they're like interleaved and all intermixed. Push doesn't care. It's fine. You can do things in all sorts of crazy orders because data flows by stacks, not by syntax. Okay, so key idea there that's going to matter when you're doing random program manipulations with genetic operators. It does complicate understanding of all programs that these things could be scrambled. So that's a little tricky. All right, here's an example that involves exec dupe, which, as I mentioned, is sort of like a do twice loop. So the program is 4.0 exec dupe, and then we've got this expression 3.13 float mult, and then 10.0, and then float div. Okay, when we run this thing, first, the whole thing gets pushed onto the exec stack, then it gets unwrapped, then the 4.0 gets pushed onto the float stack, then exec dupe duplicates the thing that will be on the top of the exec stack when it's executing, which is going to be this whole expression. So we end up with the exec stack having 2 copies of that thing on it. Okay. That means that the first one's going to get unwrapped and executed, and then the second one is going to get unwrapped and executed. And then the 10.0 is going to get executed, and then the float div is going to get executed. So it ends up computing this, where there's times 3.13 in there twice. So that's like a little module, a little function call or something that's being done twice because of the exec dupe. Okay. Now, there are a bunch of different ways to do things like recursion or loops, and here is a way to do a factorial using one of the high-level looping structures that we have. I won't go through that in detail, but we end up with the factorial of 8 in a fairly human way if you're writing it with a loop. Here is a very messy way, but it might be instructive to take a look at how you can do some fancy things in push. So I mentioned the exec stack. I didn't mention the code stack. In most implementations of push, we also have a code stack, which, like the exec stack, holds code, but is not used for the execution loop. So it's just like a scratch space for code, and you can put code there, and you can you might have code manipulation instructions that combine multiple chunks of code into one chunk of code, that reverse chunks of code that add and delete. You could have a general list manipulation library that lets you manipulate code, and we do have that in Clojush. And here's a version of factorial that does recursive calculation. There's a recursive call in there. And all of this is being done via the code stack. So a little bit of a brain teaser to figure out how that works, but maybe gives you a hint of some of the things that evolution might be able to play with. Okay. Here we have an infinite loop that is terminated by the evaluation limit. So we're putting 0 on the integer stack and true on the Boolean stack, and then we're doing a while loop. The while loop, exec while, the body of it is 1 integer add and then true. And the true is at the end of every loop, it's pushing a true. So the while, when it goes back to the while, it's always going to have a true on top of the exec stack. Again, there's no separate while control structure. It's just an exec instruction that looks at the values on the stacks. And it's going to go until it hits the limit, and it's going to end up in the configuration I ran it in with 199 on top of the integer stack. That's how many times it added 1 before it hit the limit. And in our implementation I'm using here, it also returns an abnormal termination result. So you could decide what to do, whether you care about that 199 or whether you're going to penalize this program or whatever. Here's a program that uses the input instructions I mentioned before, and we're going to run it with 2.5 already on the input stack. And this is going to compute the area of a circle with whatever radius you put in there by pushing that input twice and multiplying them, and then pushing pi and then multiplying. Okay. And here, this code, this is how you would do it in Clojush. This is how, instead of just giving it an empty push state to start with, we're giving it an empty push state onto which we've pushed 2.5 onto the input stack. Okay. All right. We have gone through now the core mechanics of push, the structure of the language. I hope I've given you a feeling for how it works and how you could go about implementing it, or if you want to use an existing implementation, what you should be looking for and why you might want to use it. What I'm going to show you now for the remainder of this tutorial is how it works within a genetic programming system and some of the results that have been produced using it within genetic programming. And I will conclude with a little bit about this metagenetic programming kind of work that push lends itself to, I think, more naturally than some other genetic programming methodologies. Okay, so first of all, genetic programming. General idea is you start with a population of random programs, you assess them all. If you're doing a generational genetic programming system, you select better programs, you vary them, and then you go back and assess the results of that variation. Okay, so if this is a generational GP system, you have a population here, you assess everybody in the population, you select parents and vary those parents or pairs of parents to produce children, to produce an entire new generation of offspring. You assess them, and you go around this loop until you either get something that is assessed to solve the problem completely, or until you hit some limit of your resources, at which point you output your best program, and that is a program that solves the problem you want to solve. Now, one of the things that you have to worry about in a genetic programming system, aside from how you're going to represent your programs and how you're going to execute them for assessment, is how you're going to vary them. And in tree-based genetic programming, people typically vary their programs by replacing subtrees with new random subtrees as the primary form of mutation, and replacing or swapping subtrees between programs as the primary form of crossover. People have developed genetic programming systems in a variety of other non-tree-based languages as well. And Push was initially used for program evolution using the standard tree-based kinds of genetic operators. Push programs look sort of like symbolic expressions used in tree-based genetic programming. You have nested sub-expressions, and the initial PushGP systems replaced random expressions with new random expressions, or swapped sub-expressions between push programs. However, much research in the field on many different representations, including machine language genetic programming and some grammatical evolution work and other kinds of genetic programming, led our group to an appreciation of the power and flexibility and advantages of working with linear genomes. One aspect of this I will point out is that there's a lot of work in the early days of genetic programming on the fact that the traditional genetic operators, mutation and crossover subtree-based operators, when applied to tree-based programs, often produces programs that grow without bound, okay? So-called bloat, and there's quite a literature on this. And there's quite a literature of ways to combat bloat. I don't want to get into that here, except to point out that this is a problem that I believe stems largely from the choice to go with tree-based programs and subtree-based genetic operators in the first place. If you have linear genomes and what I'll show in a minute, uniform variation operators operating on linear genomes, you don't get the same kind of problems, at least not nearly as severely or readily. So it would be a different and longer talk to fully dive into why linear genomes are useful, but I do believe they are. And I believe that no matter what genetic programming system you're looking at and what kinds of programs it evolves in what language, you might want to look into having the genetic operators, the variation operators, operate on linear representations of the programs. The tree-based ideas were, very helpful at the beginning of the field, but I do think they lead down some difficult paths, and that I prefer to avoid going down the path rather than to figure out how to save yourself once you've gone down the path. Okay, so linear genomes, they support uniform variation, which I think is an important concept I'll say a bit more about in a minute. They can provide structure where you want it rather than where the genome specifies that it is, via translation from the genome to the program. I'll show you a bit more about that in a minute. With push program evolution, again, we started by doing manipulation of them as trees, essentially, as sub-expressions, and replacing sub-expressions. But once we came to appreciate the value of linear genomes, we came up with a couple different schemes for representing push programs, which are these nested things, but representing them genomically as linear sequences. And that's what we perform our genetic operators on, and then they get translated to the nested expressions for evaluation. We have two schemes for this historically, one called plush, where it's like push, but there's an L for linear stuck in there. And one called plushy, which is sort of like plush, but simpler. So it's not quite plush, but it's plushy, right? Somewhat frivolous names. I hope you'll excuse that. The plush system uses what we call epigenetic markers on a linear sequence to say where the parentheses go. And the plushy system uses these close instructions inserted in the linear genome to say where the parentheses go. These are some of the systems that use plush or plushy. In fact, as of this recording, you can use either one in Clojush, and there are several other systems now, including one called Propeller I have a link to later that uses plushy. So a little bit more about uniform variation. What do I mean by that? What I mean by that is that at the variation step, all genetic material in a program that, or all genetic material that a child inherits should be approximately equally likely to be mutated during variation. That is hard to do with trees because some things are at different heights in the tree, and things deeper in the tree are more likely to be varied. No, excuse me. Well, anyway, it's hard to get the uniformity across depths in the tree. Another thing that I mean by uniform variation is that parts of both parents, if you have a two-parent genetic operator, should be approximately equally likely to appear in the children, at least if they're approximately equal in size, and to appear in a range of combinations. And the uniform variation should be applicable to genomes of varying sizes and structures. So that's what I mean by uniform variation. Again, another talk to really dig into that more deeply. But when we look at push programs, and we want to say, well, where does structure matter? If you recall the way that parenthesized expressions are unwrapped during execution, a lot of parentheses just go away and don't actually matter at all during program execution. Where they matter is when you have an instruction that manipulates code that is on the exec stack, in which case something being parenthesized means that gets manipulated as a whole. So exec dupe followed by a 3 just produces 2 3s, but exec dupe followed by open parenthesis 3 integer times blah 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 is going to close parenthesis is going to duplicate that whole parenthesized expressions. So parentheses matter mostly for defining code blocks for exec instructions. Furthermore, opening where those expressions, those code blocks should start, you can basically infer from the presence of those exec instructions. So you know when you hit an exec if that it's a good idea to have an open parenthesis after it and some stuff, and then a close. And after that close, there should be another open, and then some stuff, and then another close. Okay. So what we have done in our linear representations of push programs in both of these schemes, Plush and Plushy, is to put in, during translation, put in the opens when you translate an exec instruction. And what we do is we make a little table for our instruction set that for every exec instruction that should be followed by code blocks, we say how many code blocks it's followed by. Okay, so we just have an annotation that says exec if should be followed by 2 code blocks. Exec when should be followed by 1 code block, and so forth. We have a linear sequence of instructions and literals. That is our genome, our linear genome. And then when we go to translate it to a program, anytime you translate an exec if, you add an open. And you also remember that when that open gets matched, and there might be other nested stuff that happens in there, but when that open gets matched during translation, add another open, right? Because exec if should be followed by 2. So that's where the opens come from. They come from the instructions. Where do the closes come from? That's the difference between the Plush representation and the Plushy representation. So in the Plush representation, we add on to the linear sequence of instructions and literals, we add these, what we call epigenetic markers, which say how many parentheses should close after you translate this guy. Okay, so after I translate this exec if, I'm going to close 1 parenthesis. Okay. We also have made other use of epigenetic markers, for example, silence markers that don't get, the things that have that mark don't translate at all. And then you can have mutations that might flip the silence marker. So this was the first linear scheme that we developed. Linear sequence of instructions and literals, but they can have these markers added to them, sort of metadata added to these genes in a linear sequence. The instructions specify where the opens happen, the epigenetic markers specify the closes, and it permits uniform linear genetic operators and facilitates useful placement of code blocks. Also allows for something called epigenetic hill climbing that I will not discuss further here. Plushy is the same idea, but it's simpler. Instead of having these epigenetic markers that are sort of like attached to the genes, we still open the code blocks with based on the exec instructions, how many code blocks they should be followed by. But we allow close to appear in the program as well. And those don't get translated. They just specify if you've got something open, close it. So a close will either turn into a close parentheses during translation or into nothing if there's nothing open. Okay, and that's used in some of our systems. Okay, once you have linear operators, you can have a wide range of genetic operators that operate on linear representations. And so some of the ones that we routinely provide is a uniform mutation, where you, with equal probability for each thing in the genome, do or don't replace it with some newly generated item. Okay, alternation is a kind of crossover where you start on one linear sequence and switch to the other at some random point and switch back at some random point and so on, and you can specify the probability of switching, of alternating, and you can also specify whether or not when you switch you might move a little forward or backwards randomly. Uniform crossover is certainly possible, where you take from one parent or the other at each location with some probability. The operator that we use for most of our work these days, we call UMAD. This is uniform mutation by addition and deletion. And this is, you take two sweeps through the linear genome. The first time with some probability you add things, and the second time with some probability you delete things. This is a little different than replacing things. Replacing is like adding and deleting in the same spot. If you can add and delete in independent spots, our results seem to show you get many more paths through the search space and much better results. Again, another topic, but it's easy to do any of these linear operations once you have linear genomes. Autoconstruction, again, this is the metagenetic programming stuff I mentioned. There, if you have a data type that is genomes, then you can, and you have instructions that manipulate genomes, and your genetic operator can be in the program itself in the form of genome manipulation instructions that are in the program. And you can take the child from the top of the genome stack when you're done executing. All right, this is what it looks like to call PushGP and Clojish. So we call the PushGP function with a number of arguments here. There's an error function, and the atom generators, which is the primordial ooze out of which this particular program can be, out of which we're going to evolve programs. I'm not going to go into this in detail here. And this is where, if this was not the recorded backup video, I would actually launch a demo and we would interactively work with a push interpreter. But we're going to skip that for today. Okay, so problem solved by PushGP in that early GECCO 2005 paper on push 3, just to give you a feel for the kinds of things that it's easy to express in push, reversing a list, factorial, Fibonacci, parity, exponentiation, and a simple kind of sorting. So this is just showing that it's an expressive language where you can do a lot of standard kinds of programming problems. I'm just going to go through a couple of results that were produced using PushGP so you can get a feel for its scope. So these, again, are fairly early things. This is from 2004, but my work on evolving quantum computing algorithms was all done in Push, where we had additional types for unitary matrices. There's more to say there. I'm not going to get into quantum computing in this tutorial. Did work that won another Hume's prize in 2008 on evolving expressions in finite algebras. And there we did some of the work in Push and PushGP and some of it in tree-based GP. Most recently, a lot of the work in my group has been done on software synthesis problems, involving the kinds of programs that beginning programmers are expected to solve, expected to write, which are not very difficult programs. They're not groundbreaking in any real way, but they do involve multiple data types and loops and conditionals and sometimes multiple outputs, multiple tasks. And these problems are tricky even to frame in many kinds of genetic programming systems, but Push is well suited to it because of the expressiveness of the language and the ability to deal with multiple data types and loops and so forth without adding anything. A lot of this work was developed in particular by Tom Helmuth and his dissertation work. And there's a GECCO2015 paper with this original set of benchmarks. There's now a new one, their second benchmark, software synthesis benchmark suite that Tom and his group have developed. While people have been working on these problems in other genetic programming systems, I believe, as of this recording, that the PushGP systems still solve these most reliably, and PushGP systems are the only ones that have solved some of these problems. So this is where a lot of the research has been lately on software synthesis. Now, one more feature of Push that I want to mention is auto-simplification. So in many forms of genetic programming, you can end up with a complicated program and it's hard to know what it means. Well, that can happen in Push too, especially since Push is a pretty weird language and it can be pretty confusing to try to understand a Push program. However, with Push, it is trivial to automatically simplify programs. And the reason it is trivial to automatically simplify them is the same reason that its roots are in the fact that any arbitrary collection of items is an executable valid Push program. And that makes it so that you can hill climb your way to simpler programs pretty easily. You can simply remove something. It's not going to break the syntax. You can't break the syntax, right? Remove something or remove 2 or 3 things and test the program again. And if it produces the same results on the training data, remove a few more things. And if that breaks it and you start to get errors, then put those things back, but try removing some other things, okay? Ridiculously simple procedure here. Loop, make it randomly simpler, keep simpler if it's good or better, otherwise revert. So we routinely do that to everything we evolve. We've shown that it efficiently and reliably reduces the size of evolved programs. You can use simplification as a genetic operator. That maybe is not such a great idea in terms of evolving solutions, but simplifying, auto-simplifying the evolved result is a very good idea. And in fact, there's a GP Best Paper nominee from 2017 that shows that more often than not, much more often than not, that improves the generalization. That automatic simplification makes the evolved program more general than it otherwise would have been. Okay, here's an example working on a problem. I got success at generation 20. This is the evolved successful program. That's pretty big, size 230. There's a lot of nested stuff in there and so forth. But after auto simplification for 5,000 steps in this random hill climbing, we end up with this much shorter size 11 solution. Okay, so that's a fairly typical result from auto simplification. All right, I want to say a tiny bit about this metagenetic programming business. So in standard GP, we produce offspring by starting with a program and mutating it to produce a child program, or starting with 2 programs and crossing them over to produce a program, or straight reproduction of a program from another program. And the mutation crossover algorithms are written by humans and configured by humans. Auto construction, you put in the program itself the code to make the child. And so you execute the program to produce the child. And maybe you give it other programs as mates when you do that. Okay, that's the idea of autoconstructive evolution or auto construction. Now, in Push, you have a variety of ways to do that. In the early days, we would do that with just take the thing on the top of the code stack and say, that's your child. You have to do some tricky things to avoid pathologies like producing things that clone or are virtual cloners, near cloners, which stops evolution. And the auto construction research program has been to try to study what those constraints should be and how we can get evolution to evolve meaningfully and eventually, one hopes, do better than our handwritten genetic programming systems. It's a little more complicated when genomes are distinguished from programs, which they are in the systems I've described to you, but there you add a genome stack and you have genome manipulation instructions among the other instructions. So you evolve evolution while you're evolving solutions. You do it by having individuals produce and vary their own children with methods that are subject themselves to variation. It requires understanding the evolution of variation, and the hope is that it may produce evolutionary computation systems that are more powerful than we can write by hand. This auto-construction business is a 20-year-old project building on older and broader-based ideas by others as well. It's like genetic programming, but harder and less successful. So that's my sales pitch for auto-construction. But I do believe that in the long run, it has greater potential. Recent versions sometimes solve significant problems, intriguing patterns, and produce intriguing patterns of evolving evolution. To do this evolution squared, you have to have diversity, which means individuals vary. You have to have diversification. That means individuals produce descendants that vary in various ways. And you have to have what I'm calling recursive variance, that individuals produce descendants that vary in the ways that they vary their offspring. Okay, so you're evolving the ways they make their offspring, and that should vary. Okay, as an example, this is from a 2016 workshop paper with a non-auto-constructive run of genetic programming on one of our software synthesis benchmark problems. This is a graph of the parent-child differences over the run, and we can see, well, there's a lot of range of differences in the initial generations, but generally later there's parents and children differ by a certain amount and any amount in between, okay? So parent and child have a certain amount of difference that's capped at a certain level and can be anything in between. And that's a product of the variation operators that we used, our mutation and crossover operators. In an auto-constructive configuration that also solved this software synthesis problem, this is what the parent-child differences look like over the course of evolution. A lot more to say about this, but I want you just to notice that something is changing with the way parents produce children during evolution in this run. So auto-construction is causing evolution to evolve in some way as this problem is being solved. Many unsolved problems with auto-construction, but Push is a nice framework within which to experiment with it. Okay, so auto-constructive evolution can sometimes succeed as much and as fast as non-auto-constructive evolution, sometimes, and it has found solutions for one of our software synthesis problems before ordinary GP was able to find it. And so here are my conclusions for this tutorial. Push supports the evolution of expressive programs that use arbitrary types and control structures, possibly to perform multiple tasks. Push interpreters and the GP systems that evolve Push programs are easy to write. And Push supports research on expressiveness in genetic programming, for example, to support the evolution of modularity. I thank a lot of people, especially Nick McPhee, who helped to refine and present this tutorial in recent years. Also want to thank a lot of members of my lab and the National Science Foundation. Some references you can find in the slides, and in particular, I want to draw your attention to some of the software that we have, in particular in Clojure and Python. But if you go to pushlanguage.org, you can see some links to some other systems. Thank you so much, and I would welcome your questions, however you can get them to me. Thanks so much.